So last time we talked about public key cryptography and public key encryption, where um, between what do you call for a message being sent from user one to user two, user one uses the public key of user two, which is out there in maybe a server or something available to it. This is the server with everyone's public keys. He takes the public key, uses it to encrypt and send, right? And then the user 2 can decrypt the message using their own private key, right? And we said if we gave a description of when this is, how to define security on this, and we said that, oh, even if I define what do you call eavesdropper secure, that is the same as defining CPA secure, because any attacker, recall, eavesdropper secure, EAV secure for public key is same as CPA secure, as A has access to the public key, to PK, and can encrypt any message he wants, and can encrypt any message he wants, any message they want, right? So as a result, key exchange, what do you call? As long as key exchange is authenticated, therefore, as long as key exchange is authenticated, we can build CPA secure systems quite easily, right? Easy to build, easy to make CPA secure. Right? CCA secure was a harder question, CCA secure, and the answer to that was hybrid encryption, right? Hybrid encryption, where we saw that it was a combination of public key and private key. Public key plus private key, where we used private key to encrypt message, and then we used public key to encrypt the key for the private key. Encrypt the private key, right? And this was called the what do you call, encapsulated key method, right? Encapsulated key. Okay, so which is often written as, so this method is also called KEM, key encapsulation method. Okay, and it's called KEM paradigm. Okay, so now let us look at how we actually define a D-log based public key exchange. Okay, D-log based P K E. Okay. So what is that? What is the dialog based problem that we will be looking at? It is the Diffie-Hellman key exchange. Diffie-Hellman key exchange. And the idea was relatively simple, right? You have U1, U2. There's a group that is already out there, established very well, or U1 can send the group. U1 can generate a group and message it to U2 when they want to communicate privately. So he has to, they have to share the group, its generator of what is the size of the group Q, the generator G, and some H1, right, which is an element of the group, and U2 then sends back H2, right? How was GQH GQGH1 calculated? It was calculated by the group generation algorithm gen 1 to the n, and 1 to the n, gen 1 to the n, or g1 to the n, whatever. In which case, Q should have length n in bits, right? When you write down Q as a number, it should be n bit long, okay? How was H chosen? Well, a random X is chosen from ZQ, right? You compute then H1 is equal to G to the X, right? Send this information. User 2 computes y, which is another random element of z to the y, calculates H2 is equal to G to the y, right? And uses K is equal to H1 to the y. User 1 uses K is equal to H2 to the X, right? And now how does a message work? Well, a message that they want to send in El-Gamal encryption. So the encryption, okay, let me say this. Encryption protocol using DH problem, DH key exchange is called so the El-Gamal encryption. El-Gamal encryption. Okay. How does El-Gamal encryption work? Well, the most of the picture is still the same. You have U1 sending U2 the data, which is GQGH1, but this is the public key. Okay, everyone has access to this public key. Okay, so how does U2 send a message back? Well, the way U2 sends a message back is, well, he sends H2, or he or she sends H2, but not just that. They also send H1 to the Y times M. Well, what is H1 to the Y times M? That is exactly C2 is equal to K times M, or C is equal to K times M, right? Because H1 to the Y is your key. Okay, so I'm not writing the things down here which are same as before. Okay, so what are the steps? Gen 1 to the n, run g of 1 to the n to obtain g, q, g. Choose uniform x belonging to zq. The public key pk is equal to g comma q comma g to the x, and the private key is x. Okay. Encryption pk of m is for m belonging to g. For m belonging to g is choose I'm sorry, this should have been the encryption algorithm, so this is no longer part of Gen 1 to the m. Encryption pk of m for m belonging to g. How does this work? Choose uniform y belonging to zq. The ciphertext is g to the y c is equal to g to the y comma h to the y dot m. Okay. How does the decryption work? Decryption sk of c1 comma c2. Well, output c2 over c1 to the power x. Okay, because what is c1 to the power x? C1 to the power x is g to the xy, right? This is hy times m over h to the xy, right? Over g to the xy, maybe. Over g to the xy, right? And that is equal to just m. So it is correct. So correctness is verified. Therefore, correctness verified. Okay. But is it secure? What about the security of this algorithm? How secure is it? Well, the question is, okay, I know the Diffie-Hellman problem is hard, and that would make the key exchange hard, but now I'm encrypting the message by multiplication, right? How is that strong? Is it still the same hard? Well, the answer is, if the DDH assumption is hard for G, then the El-Gamal encryption scheme is CPA secure. Okay. I'm not going to prove it because we don't have the time. I would rather spend it to explain to you more important things. But you can show it from the Diffie-Hellman exchange, follows from security of Diffie-Hellman key exchange, or you can show it using proved directly. You can actually prove that it is perfectly secure under certain circumstances using what do you call the size of the group and I forgot the name. You look at the size of a group, size of the key space, size of the message space, and you can show that it is perfectly secure, right? So now technically the discrete logarithm assumption alone is not exactly enough. Discrete logarithm assumption is alone not enough because you need to be able to show that the second part with the group multiplication is also safe, right? And that requires you to show some other things. Okay, so in practice, the parameters GQ, so in practice, GQH are standardized and shared. GQG are standardized and shared. Okay, and the only secret key is so every user's PK just depends on their SK is equal to X. Okay, let me just do this. PK is equal to G to the X. Just depends on their SK, which is just X. Right? However, in practice, this is great, but it is slightly annoying to have to treat messages as a group element. Inconvenient to treat messages as group elements. Messages as group element. Okay, because frankly, there's a lot of message space, right? And that can be a pain. So, how do you deal with that? And the idea is, again, hybrid encryption. Use the same idea. Use key derivation to derive a key instead. Derive a key K instead, and use K to encrypt the message. Okay, so what does that mean? I.e., the ciphertext is G to the Y as before, but then it is some encryption K prime of M, okay, where K is equal to H of H to the Y, okay, where H is some hash function for some hash function H. Okay, so you're using random keys to encrypt the message. It is again combination of private key and public key, right? Instead of deriving mm, instead of encrypting as g to the y times m, um, sorry, k times m, you use it as an algorithm to get your key and then encrypt the message, right? So this can be analyzed can be analyzed by KEM HDEM paragram para, para, okay. So now the question is, how secure is it? If I take my encryption to be CPA secure, this is CPA secure, right? However, is it chosen ciphertext secure? Chosen ciphertext secure. And the problem is, no, it's not, because um, well, let me say this. El-Gamal is not. Okay, we'll talk about the security of the hybrid algorithm later. We can show that hybrid algorithms are CCA secure, because if I take my encryption here to be CCA secure, entire thing is CCA secure. Same argument as before. Okay, as for the KEM security. So as for hybrid security, we have said that it is hybrid secure. The same exact argument works here. Okay, so El-Gamal is not CCA secure. Against chosen ciphertext attacks, CCA secure. And the easy way to see this is it is malleable. Follows from the fact that it is malleable. And how do I show that it's malleable? Well, given ciphertext C1, C2, ciphertext text C1, C2, transform it to obtain the ciphertext C1, C2 prime is equal to C1 alpha times C2 for arbitrary alpha, for arbitrary alpha, and what happens if I do such a transformation? Well, what do we have? Since C1 comma C2 is equal to g to the y comma h to the y times m, if I hit that with an alpha, we have C1 C2 prime is going to be, well, g to the y stays the same, h to the y stays the same, right? What you would get is alpha times m. Right? And so while I might not exactly know what is the message, if I don't know the message m, that is fine, but I still have, if I know the message m, I have the encryption of the message alpha times m, i.e. encryption of m becomes the encryption of alpha times m, right? And that is a very big problem. For example, if there people are in a bidding war against someone, right? And you have to submit blind build attacks, right? Um, assume 2 belongs to G, which is a subset of ZP star. Okay, then and the group is G, Q, G, and the public key is H. Well, U1 bids sends the bid C1, C2, right? These are supposed to be blind bids. Like U1 should submit his blind bid, U2 should submit his blind bid. They should not know each other's blind bids, right? However, once you see C1, C2, you can send C1, comma, to C2, right? And you know that you will be making twice their bid, right? First bid will be M, and the second bid would be 2M, right? So you can change it in an expected way. How do you stop this? Well, we do this. What do you call? Ready to go. Key derivation, right? Hybrid security. That stopped it before. It's going to stop it again. So use key derivation. Coupled with CCA secure. Coupled with CCA secure private key encryption. Encryption scheme to stop to make your scheme CCA secure, i.e. ciphertext is G to the Y, comma, encryption using K of M, where my key K is equal to hash function of H to the Y, and the encryption prime is a CCA secure scheme. CCA secure scheme. Okay. This can be shown as CCA secure as long under appropriate assumptions. Under appropriate assumptions, as in when your H is a random oracle, which is a hash function, if H is modeled as a random oracle. What does that mean? My H is a hash function, right? Hash function should be should not have collision, right? But it should also be a random oracle, as in you should not be able to find what it is a hash of. If I give you H of X, right, you should not be able to find back what X was, right? If it's such a random oracle that we saw this in hash functions very, very briefly, then this entire scheme is CCA secure. So this is using the dlog scheme. Okay. What about instead if I want to use RSA based? Okay. The other problem we had seen before was the RSA problem, right? So RSA based PKE. Recall, in case you have forgotten, how does RSA work? Choose random equal length primes equal length primes p comma q. Compute modulus n is equal to p times q, right? Choose e comma d such that e times d is equal to 1 mod phi n. Well, in that case, what is happening? The eth root of x modulo n, the eth root of x modulo n is what? X to the d mod n, right? Which is because x to the e to the d is equal to x to the de, which is equal to x to the de mod phi of n, right? Which is x to the 1, which is congruent to just x mod n, right? What is the RSA assumption? RSA assumption. Given n e only, right? It is hard. So if you're given only n and e, it is hard to compute the eth root of a uniform C belonging to Zn star. Okay. So here's what is called the plain RSA encryption. Plain RSA encryption. Okay. You have a user 1. You have a user 2. They do some exchange to get things. What does user 1 do? Well, user 1 generates runs RSA generator 1 to the n, and it outputs a n, e, and d. Then the public key is ne. Ne. Private key is d. Okay. So the public key is sent, n comma e is sent. Well, what does user 2 do? User 2 encrypts the message as m to the e mod n, right? Because, well, even if you send it as m to the e, computing the message back is finding the mth root of eth root of m to the e, which is hard, right? So user 2 sends c back, and the message is then c to the d mod m. This sounds much more easier than what do you call Diffie-Hellman, right? And in that case, if I'm saying this is easier, is the scheme secure? Is this scheme secure? And we run into a trouble. The scheme, as I have written it down, is deterministic. This scheme is deterministic. Okay, and we know from before that no deterministic schemes can be CPA secure. Cannot be CPA secure. Right? So such a scheme cannot be CPA secure. And oops. So the RSA problem, RSA assumption only refers to the hardness of computing the ETH roots, right? Only refers to hardness of computing the ETH roots of uniform C. Okay. Well, the problem is C is not uniform unless M is. C is not uniform unless M is. And that means that since messages are not always completely uniform, it is easier to recover small m from C. Okay. Also, the other problem is that the RSA security, RSA encryption assumption only refers to hardness of computing the ETH root of C in its entirety. In its entirety, refers hardness of computing this ETH root of C in its entirety. RIET. What does that mean? Partial information about the ETH root may still be leaked. Might be leaked. Okay, and in fact, if you are using plain RSA, this is the case. It is the case. Case with plain RSA. Okay. And so how do you fix this? How to fix it? How to fix it? One of the ways of doing it is using PKCS number 1, version 1.5. Okay. How do you do it? You pad random amounts. Okay. Standard issued by RSA Labs in 1993. So this is the standard method for RSA padding, which is add random padding. Okay. To encrypt message M, choose random R. Okay. And my ciphertext C is equal to R adjoint E M to the E mod N. Okay. Well, great. But there's a problem. How do I figure out at what point is the message and what point is R? And that is not the only issue. No proof of CPA security unless M is short. Okay. In which case, actually, it's not that, oh, if M is short, then it is CPA secure. It's actually the other way around. Chosen plain text attacks. Chosen plain text attacks known if R is too short. Okay, so it's actually bad. We don't know if R is long, it might be CPA secure, but if R is short, it is definitely not. Sorry, if if M is short, then it might be CPA secure. If M is not short, then we know it is definitely not secure, right? Oh, chosen ciphertext attack is still possible. Okay. So that didn't work. So here's a better method. Better? Well, it is still called PKCS number 1, but now it's a version 2.0. Okay. It is optimal asymmetric encryption padding. Asymmetric encryption padding, or OAEP for short, applied to message first. Applied message first. Okay, how to do that? This padding introduces redundancy. Redundancy, so that not every C belonging to Z and star is now a valid ciphertext. Okay, which means that there is a small problem that we need to check the proper format upon decryption. Need to check proper format upon decryption, and return error if not properly formatted. Return error if not properly formatted. Okay. So how does OAP work? OAP. Well, you start with your message M and you pad it with a lot of zeros. Okay. Then you take a random element R and XOR it with G of R. You run it via H. XOR R with H of the message to get T. You XOR G of R with the message to get S, and you take both of this to the power E mod N. Okay. I'm not going to go. This sounds really confusing, and it is slightly confusing, but we are not going to go into full details because this is complicated, much more complicated and harder to compute, and B, we are short in time. Okay, so if you are curious and you want to read, you can read up the proofs. Okay, but frankly, I can't ask you to prove something like this on the exam. It's 2 days to the exam, so I'm not going to bother about it. Okay. I'll just mention that RSA OAEP can be proven to be CCA secure, can be proven CCA secure under the RSA assumption. If G and H are modeled as random oracles. Okay, and this method is actually widely used in practice. practice. Okay. Keep in mind, the factoring problem still has faster algorithms, right? So in terms of security, the Diffie-Hellman problem is going to be eventually slightly more secure than RSA problems, okay? But this is also easier to implement in a way. So, and this is widely used in practice. And I'm going to stop today's lecture here. This is the end of chapter 11. I will give you a very, very brief idea of chapter 12 tomorrow. I won't be covering it too much. It is just going to be to give you an idea of what things are, because I would like to complete the picture for public key encryption for you. Okay, it won't I won't ask anything in the exam based on chapter 12. Okay, I might ask you things based on chapter 11. I won't ask you anything based on chapter 12. But still, you should take a look at tomorrow's video also, just to know how things work. Okay, you can just listen to it once. You don't have to worry about it for the exam. Okay.